let's look at another example of finding a Fourier series. Let's find a Fourier series for the sawtooth wave. And this is the sawtooth wave that I'm going to use. You might be confused at me calling this a sawtooth wave because isn't this just a straight line? Remember, we're taking for our domain from 0 to 2 pi. And from 0 to 2 pi, the graph looks like this. But we're also assuming that outside the domain, this function repeats itself. So if once we go outside, once we go past 2 pi, this drops back down to 0, and then does the same thing, and then drops back down to 0 at 4 pi, and does this, and so on. So you can see now why it's called a sawtooth wave. It's because the graph looks like a saw, I guess. So let's go ahead and calculate the Fourier series just by calculating the coefficients by doing all of these inner products. So let's do the one for one. So take the inner product of 1 and f of x. So f of x is just, oh, I should use an x, not a t. F of x is just x, so this is the integral from 0 to 2 pi of x. So that's 1/2 x squared from 0 to 2 pi. So that's going to be, what, 2 pi squared, something like that. Not something like that, that exactly. Have some confidence, Sam. Okay, now let's calculate the coefficients for the cosine terms. Nx. Okay, so this is the integral from 0 to 2 pi of f of x is just x, so x cosine nx. So now we have to work out this integral, and you might remember from your calculus days how to do it. Use integration by parts. So this is going to give us, let's see, we're going to differentiate this one and integrate this one. So we're going to get 1 over n x cosine, sorry, sine nx from 0 to 2 pi minus integral of 1 over n, integral from 0 to 2 pi of 1 over n sine nx. So let's see, from this first piece we get 1 over n times, so plug in our 2 pi. Well, because of this sign here, when we plug in 2 pi or 0, we're always going to get 0, right? Sine of every multiple of pi is 0. So this stuff actually is always 0. Okay, minus 1 over n times integral of sine of nx. That's minus 1 over n cosine nx from 0 to 2 pi. And whenever we plug in 2 pi or 0, right, we're always getting an even multiple of cosine in here. So this is actually always going to produce the same thing as well. So right, this, so we get plus 1 over n squared. But then when we start plugging in our bounds here, we get 0 minus, or sorry, we get, it's not 0, it's 1 minus 1. Right? Because this function is the same at both bounds, and so you end up subtracting. So the whole mess turns into 0. Okay. So I guess that leaves the sine terms. So let's find the product, inner product with sine of nx and f of x, which f of x is just x, remember. So this is integral from 0 to 2 pi of x sine nx dx. Okay, and again we need to use integration by parts. So we're going to get minus 1 over n x times cosine nx at 0 and 2 pi. then minus integral from 0 to 2 pi of minus 1 over n times cosine nx dx. Okay, so what is this? So minus 1 over n times, let's see, x cosine nx at 2 pi, so we get 2 pi times cosine nx, but cosine 2 pi n. But cosine 2 pi n, that's an even multiple of pi, and so cosine of that is 1 minus, and now when we plug in 0, well, this x out in front makes this part 0. Okay, and then for this part, we can move this outside, so plus 1 over n times, and then integrate cosine nx. I get another 1 over n sine nx from 0 to 2 pi. And when we plug in 0 and 2 pi, this sine term just gives us 0. So this whole mess turns into minus 2 pi over n, it looks like. All right. And remember, let's see, we had a non-zero coefficient up here for 1. It was 2 pi squared, so let me write that one down. 2 pi squared. And then this was the inner product with sine nx. Okay, so now we can write down the full Fourier series. So first our constant term. Remember that the norm of the basis function 1 wasn't pi, or wasn't the square root of pi. It was the square root of 2 pi. So we do the inner product divided by the square of the norm times the basis function that we're on. So the inner product with 1 was 2 pi squared. The norm was, norm of 1 is square root of 2 pi, so that squared is 2 pi, and then times 1. And then for the rest of them, so this time we get every, so we get a term for every sine function. So it's inner product, so minus 2 pi over 1 over the square of the norm of the sine function, but they all have norm square root pi, so the square of that is pi, times, oh, I missed an n, right, n is 1, times sine of nx, so sine of x, plus, and then, you know, same thing for all the other terms, minus 2 pi over, the next n is 2, over the square of the norm, which is pi, times sine of 2x, and so on. So, of course, most of this cancels, so, right, all this stuff cancels, leaves a pi behind, plus, minus, sorry, minus, and then all the pi's cancel from all of these guys here. So 2 over 1 sine x minus 2 over 2 sine 2x minus 2 over 3 sine 3x, and so on. So pi, we could write this as minus 2 times the sum from n equals 1 to infinity of, I guess it's going to be 1 over n times sine nx. Okay, so let's look at what this gives us when we graph this thing. So again, remember the sawtooth function that we started with, the graph looks like this. So now let's enter this Fourier series. So the constant term, remember, was just pi. So pi minus 2 times sine of x. Okay, that doesn't look very much like that sawtooth, but let's do a few more terms. Minus 2 over 2, so 1 times sine of 2x. Okay, now it's starting to look kind of like that sawtooth wave. So minus 2/3 times sine of 3x minus 2/4, which is just half, times sine of 4x. You can see the more terms we enter, the more this looks like a sawtooth wave. Let's do one more. Minus 2/5 sine of 5x. And remember, our sawtooth wave starts at 0, 0, and then goes up like the function f of x equals x until we get to 2 pi, which is just a little bit bigger than 6, and then it drops back down to 1. So, right, we are getting the sawtooth that we started with. Right? It goes up like this, and then at 2 pi drops back down to 0, and then goes up again. So, of course, we've only added a few of these terms. If you added them all together, then you would get exactly the sawtooth wave, except at the discontinuities.